Good day, everybody. So we're going to go over section 11.3 today, and we're going to go over dependent samples, pair t-test. That means we're comparing two population means. It's just that the samples are dependent. And the best way to go through a problem like this is just to jump right into a problem and explain everything to you. So let's go ahead and do that. Pharmaceutical company created a new medication to help lower total cholesterol. The company measures 15 people's cholesterol before and after they are given this new experimental medication in hopes of getting FDA approval. The following are the data for the 15 random individuals. So think about this is that we have two populations. We have individuals before the medication. We have individuals after the medication. And what are we measuring here? Our underlying variable is what? It is cholesterol. Cholesterol is quantitative, so that means we look at means. And clearly we have a paired t-test here because we have individuals before and we have exactly the same individuals. It's just that after the medication, and we're going to compare those cholesterol levels. And so here's the data. And so take a look here that we have the data before, then we have the new pill, and then we have after. Okay, and so for the first person, they had a cholesterol of 243. It lowered down to 201. All right, for the second person, 234, and then 207. And what has intervened? That pill. All right. All right. So notice here I've created a difference column, the D's. Okay, I've created a difference column, call them the D's, and the D's, like I have here, is simply before minus after. And so what you want to think of here is that we have a minus sign here and an equal to sign here to calculate the differences. And so notice the difference for the first person would be positive 42. Okay, positive 42. We'll get to that here in a second. Now, if you do that for each one of the individuals, what you have done is you have taken two populations, the before and after, and when you do the subtraction between the two, what you have done is you've created one new random variable, the D's. And that's the new random variable here. So that's kind of unique here. We started with two populations. We started with two sets of data, but when you do the subtraction between the two, you've created just one new random variable. And so all the analysis will be done on the D's, on this new random variable, even though we have two populations. That's kind of unique. It's kind of different. So, like I said, for the first person, we had a difference of 42. All right. For the second person, 27. Now notice here, the third person had a -2. Positives and negatives mean a world of difference here. All right. Makes a big, big, big difference. Now I filled in the rest of the data there. All right. But what I encourage you to do is the following. There's a major step here when you do a pair t-test, and it's the following. Because if you do this, it will make your lives so much easier if you just simply do this next step. Now, I don't care if you do it in your head or if you do it, write it on a piece of paper while you're doing the problem, but I highly encourage you to do this step. Do not skip over it. And what it is it's all it is defining what a negative D means in terms of the problem and what a positive D means in terms of the problem. And all you're doing is using common sense. You're not using any math. You're just using common sense. Let's take a look at the first person. So the first person says that they had a cholesterol of 243. Then they took this pill and it went down to 201. Is that a good thing? Ask yourself, is that a good thing? This is the common sense. By taking this pill and the cholesterol lowering, going from 243 and lowering down to 201, was that a good thing? Yes. So a positive D means what? That the cholesterol lowered and that the pill was effective for that person. So every time you see a positive number, the pill was effective for that person. All right, so on and so forth. However, what does a negative D mean? A negative D meant, well, let's take a look at the third person here. A negative D meant that the cholesterol actually increased. That's a bad thing. So every time you see a negative D, that is suggesting what? That is suggesting that the pill certainly did not help and actually could have hurt in some ways. All right. Please do not skip that step. All right. So that was the only place a negative D occurred. Okay. So negative P means that, excuse me, a negative D, sorry, I said P. Negative D means that the new pill didn't work for that individual. And a positive D, which is every place else, the pill did work for that individual. And if you keep this in mind, this negative D and positive D, this idea, things will be so much easier going forward for you. You'll see why. Let's keep those two ideas up on the screen here. So if the mean difference for the entire population, so I'm not talking about the 15 people here, but everybody who has high cholesterol and took this pill, all right? So if the mean difference for the entire population is positive, meaning greater than 0, this would show that on average the pill is effective. Why? Well, because every time that we saw a positive D, that means it was effective for that individual. So if you see a positive D for the entire population, not just the 15 people, but for the entire population, all right, this would show on average the pill is effective. What we're going to call that mean for the entire population for the differences will be mu sub D. That makes sense, because what is mu? Mu is the population mean. And so this would be the population mean, but for all the differences. Okay, a little mu sub D here. All right. So that is the parameter that we're going to make a confidence interval for. All right. That's the parameter that we will make a confidence interval for. And what you got to think of is mu sub D is the following. All it is mu1, which is the mean cholesterol before for the entire population. Mu2 is the cholesterol level after for the entire population. And we're just doing the subtraction between the two. And so mu1 minus mu2 is simply equal to mu sub D. And so that's one way to think of it. Another way to think of it is that it is the average difference, all right, but for the entire population of pill, people with high cholesterol that's taking this pill. All right. So when I say that D is the new random variable, the entire analysis is going to be based upon the D's, all right? But it'll effectively compare mu1 versus mu2, and I'll show you how. So if we can show, so I'm right down here, if we can show that mu sub D is greater than 0, we are showing that the new medication is effective in lowering the population's cholesterol on average. Okay, we're not saying for each individual, but on average, the pill was effective in lowering cholesterol. All right. So what is the corresponding statistic? If this is our parameter, what's the corresponding statistic? The corresponding statistic is D bar. Well, what was X bar? What was X bar? X bar was sample mean, right? What do you think D bar is? It's the sample mean just for the differences, right? And so D bar is the average of from our sample. So in this case, the average difference for the 15 people. We can go ahead and calculate D bar. And so it's no different than any other average. You would add up these guys here, the D's, and divide through by N. N is the number of natural pairings that you have here. So we had 15 natural pairings, so N is 15. And so we got 20.8. Now let's think about what this means. It turned out to be a positive 20.8. Turned out to be a positive 20.8. So what does that mean? On average, the cholesterol actually lowered by 20.8 units. All right, that's important here. That's why we were defining what these mean in terms of a negative and a positive. Since we got a D bar that's positive, could we have gotten a D bar that was negative? Of course. But here we got it to be positive, and that means that the cholesterol actually what? Lowered after taking the pill. Now, can we take these results for just these 15 people and apply it to the entire population of everyone who's going to be taking this new pill, this new medication? Well, we have to see. So it says here, calculate a 95% confidence interval for the population mean difference, assuming the differences are normal. All right. So here's the formula for mu sub d. It's d bar plus or minus. Remember, every confidence interval has to have a plus and minus sign in it. So we have d bar plus and minus critical value that's in terms of the t distribution. Now that should not surprise you. That shouldn't surprise you. And I'll explain why here in a second. Then we have the standard error as the standard deviation of the D's. So it wasn't well, that's not showing up very well on the screen. So what this is a standard deviation of the D's. It's S sub D divided by the square root of n. All right. Now, this formula should look awfully familiar to you without thinking about it too much. Remember when we made a confidence interval for just simply mu? So when we made a confidence interval for mu, remember the formula? We had x bar plus or minus the critical value that was in terms of the t distribution times the standard error, which was s divided by the square root of n. Sound familiar to you? I hope it does. All right. Notice here it's exactly the same formula as this guy over here. It's just that instead of our random variable being x, which is usually what we think of when we think of the sample standard deviation, that this is in terms of simply x, all right, we have the d's. And so instead of having x bar, we have d bar. Instead of standard deviation of the x's, we have the standard deviation of the d's. Notice still the square root of n, right? And still the critical value. All right. And so this critical value is still coming from the t-table. Remember the degrees of freedom that we had when we were just looking at a confidence interval from mu? It was simply what? N minus 1. It's still N minus 1 here. It's exactly the same process because why? We went ahead and created just one random variable and we're analyzing the mean, the population mean, for just one random variable. It should be exactly the same formula. It's just that instead of the d's, instead of the x's, we have d's. That's all. Same exact thing. So I believe that the next slide is going to look up the critical value. So let's see, we had sample size of 15. That means our degrees of freedom is what? 14. So we got to look up 14 degrees of freedom at a 95% confidence level. All right, so 14 degrees of freedom, 95%. I got here 2.145 for a critical value. All right, and so I think we have everything in order to create our confidence interval. All right, we got 2.145, we got d bar, we got the standard deviation of the d's, and we got square root of n. Oh, that's right, the standard deviation of the d's. Okay, I did not give you that yet. My mistake. I forgot that I had not mentioned that yet. And so what exactly is that? It's just the standard deviation of these numbers, right? That's all it is. So a lot of the problems in the text does not give you the standard deviation of the d's and make you calculate them. I think that's ridiculous. We have already tested you on how to calculate a standard deviation. It's just the standard deviation of those numbers. So either put them in a computer, into a calculator, or we're going to give them to you. Here, I prefer just to give it to you, or we'll calculate with a computer. So I gave it to you, and it turned out to be 12.5. All right, 12.5. All right, so I think we have everything now. And so let's go ahead and calculate our confidence interval. So we have 20.8 plus or minus the 2.145, our critical value. Our standard error is 12.5 divided by the square root of 15. Remember, put in n, not the degrees of freedom. So it's 15 for n. So 6.92 turned out to be the margin of error. I applied the margin of error to the point estimate of 20.8, our d bar. And what do we get? We got 13.88 to 27.72. And so we have to figure out what exactly that means. Now, if you can already figure out what this means, bear with me because I have about 3 or 4 slides following that is going to explain exactly how we should interpret the confidence interval in this section and the following section when we do a 2-sample t-test. So bear with me. If you don't know exactly what this means, the next 4 slides are for you. All right. So to start this off, we think mu sub d is located somewhere between 13.88 and 27.72. So what exactly does that mean? So if the confidence interval is entirely positive, notice our confidence interval was entirely positive here. Okay. It went from 13.88 to 27.72. What that suggests to us is that mu1 is greater than mu2. But why? Why does it mean that? All right, let's simplify things. Think about like this. If I told you that we were to take the difference between two numbers and I told you the difference was positive, what does that mean about the value about value 1 and value 2? So we got two numbers. We take the difference between the two, and the difference turns out to be positive, meaning greater than 0. All right, well, let's actually use a number here. That sometimes helps. Let's say that the difference turned out to be 3. We know then the first value is what? Greater than the second value by 3 units. Okay, for instance, this could be 7, this could be 4. We know 7 is greater than 4 by 3 units. So if we know this number right here, okay, is going to be a positive number, we know that the first number is going to be greater than the second number. All right. That value is what we're creating a confidence interval for. So we are not making a confidence interval for this number. Nope, not this number. We're not making a confidence interval for this number. What we're making a confidence interval for is that number right there, the difference between the two. So for instance, let's say our confidence interval turned out to be 6 to 14. The first thing that you should pay attention to is that since the entire confidence interval is positive, this indicates that the first number, mu1, this number right here, so if this was mu1, this is mu2, okay, we know that was supposed to be a 2. All right, we know that mu1 is greater than mu2 anywhere from 6 to 14 units, okay? And I just told you that mu sub d is equal to mu1 minus mu2. So if we go through this process of doing a paired t-test and our confidence interval turns entirely positive, that tells us that whatever was in the first population, its mean is greater than the mean of the second population. All right. All right, let's continue. Let's say that the entire confidence interval is negative, meaning, and what that is suggesting is that mu1 is less than mu2. So we go through the same thing where we do the difference between the two, and we simplify with just simple numbers right now. And I told you the difference was negative. What does that mean about the value of one, about the value of the first number versus the value of the second number? All right, so we got two numbers. All right, turns out to be negative, the difference, less than 0. So let's say that it turned out to be a -5. This is the value that we're creating confidence interval for. It's this guy here, okay? Not this one, not this one. We're creating a confidence interval for this number right here, all right? And let's say that the confidence interval turned out to be a -16 to a -7. Now be careful. This indicates that mu1 is less than mu2 anywhere from 7 to 16 units, and yes, I did not make a mistake there. English-wise, when you use the word less than already, that mu1 is less than mu2, you would go ahead and drop these signs, and then you would state it as the lower number first, and then the higher number. So you, for instance, okay, let's say that you had here 4 and 9. Now listen to what I say here. 4 is less than 9 by 5 units. You would not say 4 is less than 9 by a -5 units. It doesn't make it. You would just drop the negative sign because if you use the word less than and a negative, you actually mean positive. All right. And so 4 is less than 9 by 5 units. So you drop the negative sign when you use the word less than. And then you want to make this read like a number line. And so you put the lower number first and then the higher number second. But the key here is that if you had an entirely negative confidence interval in this section or the following section, that's telling us something very specific. Okay. What is it telling us? Specifically, it's telling us that mu1 is less than mu2, anywhere from this range of values. Okay, we can have a third option, third thing happen to us. What happens if the confidence interval is a negative for the first number and a positive for the second number? So for instance, it turns out to be a -5 to 9. What does this mean? Well, right off the bat, what that's telling us is that we aren't sure if mu1 or mu2 is larger. You just don't know. Now why? What is the -5 indicating to us? Well, what this is indicating is that mu1 could be less than mu2 up to 5 units. What is the positive 9 telling us? This is indicating that mu1 could be greater than mu2 up to what? 9 units. Okay? Well, the interval also contains the value of what? 0. What is that telling us? Is that mu1 could be equal to mu2. And which one is correct? Is it this one? Is it this one? Is it this one? And the answer is, I don't know. We don't know which one it is. Okay, it's not conclusive. All right, and so we don't know what's going on here. And researchers have to realize that you're going to run into this every once in a while, actually quite a bit. Okay, that you're going to get inconclusive results, that you cannot tell a difference between these two means, these two population means, based upon the random sample or samples that were taken. Okay. So let's go back to our example here. All right. And I summarized the results, what I just talked about here. All right. So if the confidence interval is entirely positive, that's what that means. If it's entirely negative, that's what that means. If it goes from negative to positive, it's inconclusive, and we don't know which one it is. Okay. So I've summarized it right there. Okay. Now let's take a look at our confidence interval. Our confidence interval went from 13.88 to 27.72. Our confidence interval is entirely positive. Since it's entirely positive, mu1 is what? Greater than mu2. Okay? And our conclusion, we'll just state that. We are 95% confident that the new medication on average, so what does that mean? So let's see. Before going too far into the conclusion, let's go back up here. Here's mu1, here's mu2, right? And we think that the before cholesterol is greater than the after. And what does that mean? A positive D meant what? That the pill was working to lower cholesterol. So notice what I put here. We are 95% confident that the new medication on average lowers cholesterol anywhere from 13.88 to 27.72. Maybe I should have put the word units there. For all people with high cholesterol, that is, that's going to be taking this pill. Okay? So there you go. There's example number 1. All right. We'll go through a second example. We'll go a little quicker here. Oh, my mistake. There are conditions. Remember I told you for every inferential technique, there are conditions. Okay. I kind of skipped over the conditions, but we need to go over them. All right. However, remember I told you that this is exactly the same confidence interval that we were creating before. And so these conditions should sound awfully familiar to you. Okay. It's just that instead of applying to X's, they're applying to D's. One, we need a random sample or an experiment. So we need some sort of randomness. Okay. So the company measures 15. Hopefully they did this randomly. Okay. And then 2, either we need the D's to be normal. Okay. Now before, when we were doing this, it was we needed the X's to be normal. Well, here, what's the new random variable? The D's. So we either need the D's to be normal, or we need n to be greater than or equal to 30 for the central limit theorem to apply. Now, notice what I put here is that when we calculated 95% confidence interval, when I wrote the question the very first time, and you go back to that slide, I said, assuming the differences are normal. Okay, so the D's are normal. So this part of this condition applied. Okay, and here's the thing: is that if going through this example, it's very possible that if we go through these numbers, meaning we have you calculate the D's like in WebAssign or something, it's very possible that N is not going to be greater than or equal to 30. That's a lot of calculating for you guys to do. Okay, and so if we want the second one to apply, we probably would have to summarize like D bar for you and make sure that you understand everything that's going on with the problem, because you would not be calculating the D's then in that sense, because it's too much to calculate. Okay. All right. Now, in either situation, in both cases, what that would mean is that the sampling distribution of the D bars would be a T distribution approximately normal. That should make sense to you, because before it was if either case applied, then the sampling distribution of X bar. So if you put all the X bars together, it formed a T distribution. Well, if you put all the D bars together into a distribution, they would turn into a T distribution here. Okay. This is actually step number one. And so when we do problem number two, this is actually going to be the first step. Okay. Then we'll do the everything that we did before. Okay, here's example number two. I randomly select 12 students who did not come to my office and decide to retake the test without knowing what mistakes they made. Oh, I probably should have said decide. All right, so now here's the background in this. I didn't do the whole thing because if I try to write this whole thing out, it would have been long and too long for this page. Okay, I have a stats course that is a lot lower than this one, where the students are allowed to retake one of their exams in the semester. All right, it is not this course, so you cannot take a retake for this course. Okay, it is in another course a lot lower than this one. Okay, and so anyways, when a student does poorly on an exam, what I do is I encourage them to come into my office, okay, and we look at the exam together. All right. So we look at the question, we look at what they did right, what they did wrong, what they guessed at, so on and so forth. Okay. In hopes of that they learn from their mistakes, because part of the educational process is learn from your mistakes. All right. Well, these students right here that I randomly selected, they decided not to come into my office and take a look at their first attempt. Okay. And the reason why they wouldn't see these results is because it's not graded on a piece of paper and pencil. It's all on a computer. It's all on a computer. And so the computer doesn't tell them what they did right or wrong, but I can show them what they did right or wrong in my office. Okay. And so hopefully that gives you enough of a background to see what's going on here. Okay. So they took their first attempt, but they did not come into my office, and they just said, okay, let's just go take the second attempt. All right, so let's take a look here. So a negative here, a negative actually means a good thing. Okay, different than the first problem, right? Aha, that's why it's so important to define what a negative D and a positive D mean, because a negative D and a positive D can mean, doesn't mean anything good or bad. It just, and it's going to switch from problem to problem. Okay, and you got to use some common sense. Okay. So it says here, create a confidence interval for the mean difference in scores between the first and second attempts for all students that didn't come into my office. Okay, that did not come into my office. All right, to look at their first exams, assuming the D's are normal. So I kind of abbreviated there, so I had the space. Okay. All right. So define a negative D. Negative D meant what? Negative D is that the second attempt was better. So negative is a good thing here. Okay. What is a positive D? Positive D is a bad thing. All right. Like the second person. All right. It actually went down. So if mu sub D is less than 0, on average, students did better with the second attempt. Mu sub d is greater than 0. On average, for the entire population, students did better with the first attempt. That's what we're testing. That's what we're running a confidence interval for. Okay, I filled in the rest of the data there. All right. All right, let's move on. D bar. So I averaged these D's. All right, so D bar, the sample mean for the differences turned out to be a negative 1.75. Sounds good. The standard deviation of the D's turned out to be 4.26. I think it was 4.26 repeating. I just rounded to 3 decimal places, so 4.267. Right, so I gave you that. Again, that's just the standard deviation of those 12 numbers there. Here's our formula. All right, you should be familiar with the formula. We're going to have to look up the critical value. All right, so we have 11 degrees of freedom and 95% confidence interval. So 11 degrees of freedom, 95, 2.201. Okay. Okay, well, we'll have to remember that, 2.201. Then I did the conditions. All right, so either we need a random sample and experiment. Which one do we have here? Let's see, randomly. Okay, we did a random sample. Either we need the D's to be normal, okay, or we need n to be greater than or equal to, that should be greater than or equal to 30. Certainly we did not have that. In either case, the sampling distribution of D bar is a t distribution. So since that's the case, all right, we got that. That means that's why we're using the t distribution, okay, to figure things out. Okay, there's our critical value. We put it into the formula. And there's our margin of error of 2.71. We apply the margin of error to the D bar. So I get a negative 4.46 to 0.96. Okay, so notice the confidence interval is a negative to a positive. And that tells us something, right? So this is one way of saying it, and this is what I would, what most textbooks would do, and probably what most professors would do. And I hate it. I hate it. Because if you told this to somebody on the street, they would look at you pretty funny because they would have no idea what the heck you were talking about. So we could say we are 95% confident for all students who didn't look at their first attempt. On average, the score would change from a negative 0.96 points to 4.46 points with their second attempt. Yikes. Maybe some of you can figure that what that means, figure out what that means. I have a tough time, okay? It's very confusing. When you don't have a very clear cut, it's either increased or decreased. When you have something that includes the value of 0, it's very hard English-wise to write this out and make a whole lot of sense out of it. I hate writing it like this. And if you probably looked at people's research, they probably wouldn't do that, okay? They would probably just say, I got inconclusive results. So, in other words, what I want you to think, how I want you to think of it is that since the confidence interval contains the value of 0, we are not sure if mu1 is greater than mu2, mu1 is less than mu2, mu1 is equal to mu2. We don't know which one, okay? And so if they don't come into if they do not come into my office and take a look at their first attempt, does it appear to be a significant difference with their second attempt on average? Doesn't. It certainly doesn't look like a significant difference, okay? And so this sort of encourages students then, hey, you should probably come into my office, let's take a look at your exam, and probably you're going to do significantly better, okay? All right, so that takes us to the end of this section. Thank you for your time.